We now have this next question on the board to calculate the combined capacitance of the capacitor arrangement below. And this is the arrangement of the capacitor. And if you look at this capacitor, you notice some points that they are arranged in what? In parallel. Okay? Like this point between these, let's fix here to be point B, and then here to be point C. Let's call this to be point D, and this to be point E. Between points B and C, the capacitors we have there are arranged in parallel. So to solve this problem, all I need to do is to take note of these capacitors between points BC. Okay, I can call it CA. As okay, these are parallel capacitors, parallel. Then again, we have this between these 2 points, point C and E. Okay, that's point D and E. I'm going to call the resulting capacitance from here to be CB. Again, you notice that they are parallel. Okay? So I would obtain the total capacitance here, which is CA and CB. They will now be connected in series to this 3 microfarad and this 3 microfarad. So this is what we are looking forward to. We want to get something like this, where this is going to be point A, point F, 3 microfarad, CA, CB, and then 3 microfarad. So let us obtain CA and CB first. First, obtain CA and CB. Now you know that CA and CB, for CA, look at it. So CA will have parallel capacitors there because they are in parallel. So for parallel capacitors, CA is going to give us the capacitance of the 2 microfarad plus that of this 2 microfarad plus capacitance of the other 2 microfarad. This is between point B and C, between point BC. So if we do that, our CA will be equivalent to 2 plus 2 plus 2, because I have the 2 microfarads in between these 2 points, which is 6 microfarads. We've gotten our CA. We'll do same to obtain CB. So we also say that CB will be equal to capacitance of the 3 microfarad plus capacitance of the 2 microfarad connected in parallel between point DE. And this is between point D and E. Alright? Between point DE. So parallel capacitance, which results from the CB, is going to be 3 plus 2, which gives us 5 microfarad. You take note that what we now have is, we now have a diagram that looks like this point A, 3 microfarad. Then this is CA, which we've obtained to be 6 microfarad as calculated. Then CB, which is equal to 5 microfarad as calculated. And then our 3 microfarad. And at point F. So this now is series connected capacitors. So series capacitors, we know that the formula is given as 1 over the effective capacitance, that's the combined capacitance, equal to 1 over capacitance of this 3 microfarad plus 1 over CA plus 1 over CB plus 1 over capacitance of the last 3 microfarad. So if we substitute here, we have 1 over C equal to 1 over 3 plus 1 over CA is 6 plus 1 over CB is 5, then plus 1 over this capacitance, which is 3. I'm going to use the LCM method to obtain this. LCM of this denominator is 30. Okay? 30 divided by 3 will give us 10. 10 times 1 is 10, then plus 30 divided by 6 will give us 5. 5 times 1 is 5. Plus 30 divided by 5 is 6. 6 times 1 will give us 6. Then plus 30 divided by 3 is 10. 10 times 1 will give us 10. If you work out this, it implies that 1 over the combined capacitance will give us the numerator. If you add it up, is 31 over 30. From here, we can now invert. Is that okay? We'll do an inversion so that C, it implies that C is equal to 30 over 31. Therefore, the combined capacitance for this arrangement there is going to give us 0.97, that is 30 divided by 31 microfarad. And this is our result for this problem. Just look at what we did. First of all, obtain the resultant capacitance for these 3 connected parallel capacitance. Obtain also for this, which we call CA and CB. You get this series arrangement, look at it, then use our series capacitor formula to now obtain the overall capacitance of the diagram on the board. In this video, we're going to look at a question, okay, on hollow sphere of radius 2 cm carrying a charge of plus 4.8 times 10 raised to the minus 12 coulomb. We are asked to calculate the capacitance of the sphere and then the potential difference on its surface. Now, to attempt this question, first of all, let's bring out the parameters from the question. This is 2 cm, because the 2 cm is the same as 2 times 10 raised to the minus 2 meters. Dividing 2 by what? 100. Then the charge that the sphere carries was given to us to be 4.8 times 10 raised to the minus 12 coulomb. We have to calculate the capacitance of the capacitor, we don't know. Now for a charged sphere with radius, okay, we already derived the equation that the capacitance of such sphere is giving us 4 pi E naught times R. Is that okay? E naught times R. The E naught is permittivity of what? Free space, which is 8.85 times 10 raised to the minus 12 farad per meter. So we can substitute there directly, and then capacitance will give us 4 times pi, then times pi there 3.142 or 22 over 7. Then the permittivity of free space is 8.85 times 10 raised to the power minus 12 times the radius of the sphere, which is 2 times 10 raised to the power minus 2 meters. Now if you solve this out, let's see what we're going to get, okay? 4 times 3.142, we're going to multiply by 8.85, then multiply by 2. From here, it's giving me 222.45, then times 10 raised to the power. We can add the powers of 10 here. That's going to give us minus 14. Okay, now if you work in this by moving points, this is in farad already, but we can still move our point 1, 2, so have 2.22, then times 10 raised to the power. We'll move the point 2 times to the left, so we're going to add 2 to this minus 14, which will give us minus what? 12 farad. Does that make sense? This is the same as 2.22 picofarad. Remember, 10 raised to the power minus 12 is pico. And we're going to leave a result in farad. But please take note, suppose this sphere is placed in a given medium, and then the dielectric constant value of that medium is given. What will this formula become? We won't just use E naught, we won't just use permittivity of free space. We're going to use the permittivity of the medium. Where in that case, we know that our permittivity of the medium will now be the dielectric constant relative permittivity times the permittivity of free space. We're going to substitute it for this permittivity of free space there. So take it. Now let's look at the second part of the question. We have to calculate the potential difference on its surface. We don't know. There's electrical potential, but you know that the relationship between electrical potential and capacitance with capacitor to charge. We have it as, so we're going to say recall. We have it as V is equal to 1 over 4 pi A naught. And this is a constant, so we're going to multiply by what? The charge divided by the distance, okay? That is the radius of the sphere. Of course, this equation, you know, is still the same as writing V is equal to Q over what? C. Does that make sense? So either of them you use, you still get the same result. If you're using this, 1 over 4 pi A naught is 9 times 10 raised to the power what? 9. Take note of that. Then multiply by the charge divided by the radius. So I'm going to use this formula, okay? They will still give you the same thing. So you can work it out using this. But take note 1 over 4 pi a, that is a constant, 9 times 10 raised to the power what, 9. Let's substitute here and see the charge on the sphere is given to be 4.8 times 10 raised to the power minus 12 coulomb, and then divided by the capacitance, which we already calculated to be 2.22 times 10 raised to the power what, minus 12 farad. Of course, the potential difference, or electrical potential in this case, what's going to happen here, this and this will go off. We're going to have 4.8 divided by 2.22. So from my end here, it's giving me 2.16 volts, alright? So this is the potential difference on the surface of the sphere, whereas this is the capacitance of the sphere.